The next type of induction problem to look at is divisibility. I've labelled it 3 because it's sort of really carrying on from yesterday. Prove that n times n plus 1 times n plus 2 is divisible by 3. Logical when you think about it, because if you have 3 consecutive numbers, clearly one of those numbers must be divisible by 3. But let's prove it. So start off, prove it true for the first case. Now this one, there's not a left-hand side or a right-hand side. I'm simply saying, all right, well, let's sub 1 in. I get 6, yes. 6 is divisible by 3, so it works for the first case. So I'm now going to assume it's true for n equals k. The way I write the assumption down is because I want to say it's a multiple of 3. Well, the way of doing that is saying, well, k times k plus 1 times k plus 2 is equal to 3 times something. But obviously that something has to be a whole number or an integer. And by the way, some people think that p should be a positive integer. That's not true, because -6 is divisible by 3. So what do we want to prove? I want to prove it's true for the next case. So that k plus 1, k plus 2, k plus 3 multiplied together to give 3 times something. I don't write 3p down again because it's unlikely they're going to be equal to the same thing. So I just pick another letter, q, where q is some integer. Let's do a proof. So we're starting with this algebraic statement. We want to show it's 3 times some integer. We want to get the assumption in there. Have a look at our assumption. Our assumption has k times k plus 1 times k plus 2. So I'm going to leave those two things factored together. So basically I'm expanding the k plus 3. And that's how I'm going to get the assumption in there. I've got my assumption, k plus 1, k plus 2. And that is our assumption, 3p. The other one is 3 times k plus 1, k plus 2. So I can factorise that with 3. So 3p plus k plus 1 plus k plus 2. Well, that's got to be an integer. Because if I add 1 to an integer, I'm going to get an integer. If I add 2 to an integer, I'm going to get an integer. Multiply 2 integers together, we get an integer. And then p plus an integer, that's going to be an integer as well. So it's fine, that is indeed an integer. Hence the result is true for k plus 1. If it is also true for k, etc., etc., etc. Here's an interesting one where it's divisible by 5, but you'll notice there's 2 numbers there rather than one thing. So 3 to the power of 3n plus 2 to the power of n plus 2 is divisible by 5. Prove the result is true for n equals 1. Okay, 3 cubed plus 2 cubed gives me 35. Yep, that's divisible by 5. So all good. I'll assume it true for k. So 3 to the power of 3k plus 2 to the power of k plus 2 is 5p. We're going to prove it true for k plus 1. So 3 to the power of 3k plus 3, 2 to the power of k plus 3 is 5q. All right, here's my proof. How do I get the assumption in this time? I'm going to break up either the 2 or the 3. It doesn't really matter which one. I'm going to break up the 3. Now in the assumption we had 3 to the power of 3k. So I'm pulling out 27 there. So I get 27 times 3 to the power of 3k. That allows me to substitute in the assumption, but the assumption rearranged. So the assumption was that 3 to the power of 3k plus 2 to the power of k plus 2 is equal to 5p. I've just moved the 2 to the power of k plus 2 to the other side of the assumption. So now I can substitute in for 3 to the power of 3k, 5p minus 2 to the power of k plus 2. We're trying to get a multiple of 5. Okay, well, 27 times 5, 135. I then have 27, or negative 27, lots of 2 to the power of k plus 2, plus 2 to the power of k plus 3. But hang on, that 2 to the power of k plus 3, I could rewrite as 2 times 2 to the power of k plus 2. So now, how many 2's to the power of k plus 2 do I have? Negative 25. 5 goes into negative 25, so we've got it. It's 5 times some integer. And in this case, I know it's an integer because 2 to the power of an integer must be an integer. So hence that one's true. If, of course, my assumption was correct. But since we proved it for n equals 1, we know it's true for all integers. Let's look at a really interesting one. Got to be careful with this one because it's a polynomial. So we're saying x to the power of 2n plus 1 plus a to the power of 2n plus 1 is always divisible by x plus a. Prove it true for what? Well, I get x cubed plus a cubed, which is the sum of two cubes, and I certainly know the sum of two cubes has a factor x plus a. So yes, that one works. My assumption, okay. Notice here, I'm multiplying x plus a times qx, not where qx is a integer in this case, we're dealing with polynomial. So now I'm assuming qx is a polynomial. Prove it true for k plus 1. So I'm going to prove it that x to the power of 2k plus 3 plus a to the power of 2k plus 3 is x plus a times some other polynomial, which I've called tx. So I want to get that assumption in there somehow. Similar to what we just did, but now I'm doing it with algebra. So the x to the power of 2k plus 3, I'm going to rewrite as x squared times x to the power of 2k plus 1. That will allow me to substitute in the assumption, rearranged. If I make x to the power of 2k plus 1 the subject of our assumption, then we'll get x plus a times qx minus a to the power of 2k plus 1, and then we've still got the plus a to the power of 2k plus 3 as well. So what do we got when we expand that out? Well, my very first term, I've got x plus a as a factor, that's good, but I'm left with minus a to the power of 2k plus 1 x squared plus a to the power of 2k plus 1 a squared. So all right, that's got a common factor of a to the power of 2k plus 1. And I'm left with x squared minus a squared, difference of two squares. And so yes, it has a factor of x plus a when we play with the difference of two squares on that one. So hence, we can say it's x plus a times some polynomial. That polynomial in this case happens to be x squared times qx. That's all right, multiply a polynomial by x squared, it's still a polynomial. Minus a to the power of 2k plus 1 x minus a. So yep, that is a polynomial, it's not a problem. Hence it's true, etc., etc. All right, shall we play with some divisibility problems? Here we go. Oh look, if I was to write that conclusion in set notation, all integers n greater than or equal to 0. That's if we were starting with n equals 0. Well, asked a similar one yesterday, was what happens if we start with n equals 2. So same sort of idea. For all integers n is greater than 0, I would write for all n, an element of the integers such that n is greater than or equal to 0. It's possibly just easier to write for all integers greater than, yeah. Yeah, if it was even integers, so for even ones, I'm writing for all n elements of the integers, n is greater than or equal to 0, such that there exists an a, also an element of the integers, where n is equal to 2a, thus making n an even number. Yes, it's quicker just to write for all even integers.